behind.
No, not one. And I was like, where was that? I was like, which one?
Yeah.
It's 8:30. Sounds like it's like, it sounds like the sun is like, she's confusing now to be safe.
So, second part of inferential statistics focuses in on what is known as a hypothesis test. What's a hypothesis? Essentially, it's an educated guess. There's technically a little bit more that goes into that, but layman's term, it's an educated guess. So, yesterday we started this idea of inferential statistics, which really is the purpose of why we do statistics. The purpose of statistics is for us to try to get an idea of what it is that is going to happen in the future based on what has happened, or it's to make assumptions about larger groups based on smaller groups. Now, we're focusing more in on that piece, taking a sample to figure out things about the population. Yesterday, we worked with confidence intervals, this idea of figuring out where a true population's mean is based on a sample population's mean. So making that assumption from small to large. The other thing that we can do with inferential statistics is to work with this idea of essentially proving that something isn't going right. It's the other piece of inferential statistics. There are plenty of situations in the world where someone steps forth and says, this is what is happening. And that you kind of look at it and say, I don't think that's right. And that's where hypothesis testing comes into play. In the world, experts say things all the time. And generally speaking, we want to step in and we want to show that they are wrong in situations where we're seeing it doesn't match up. Hypothesis testing is used for that express purpose. Hypothesis testing is a process used to test a specific claim. Now, when you are trying to test a specific claim, when you are trying to step in and say the expert is wrong in what they are saying is supposedly true, you have a disadvantage. You're not the expert. The experts generally have more data, they have access to the actual population, and they can tend to get more information. So as a result, when you are doing a hypothesis test, you have to come in with a lot of evidence that disproves their claim because you are not the expert on the matter. They are. And so hypothesis testing does exactly that. It comes in and says, I've got proof. I've got proof that there is no way you are right. And the way that you prove that they are not right is you have so much evidence that essentially says, what you're saying only has a 5% possibility of actually being true. Therefore, that is enough to prove that you are wrong. In order to go through and do a hypothesis test, essentially what ends up happening is there are technically two hypotheses. One of them is known as the null hypothesis. It's denoted by H sub O, H sub 0. The null hypothesis is considered to be the neutral claim. It is the statement that nothing is wrong. It's essentially the statement that the expert knows what they're talking about. There's one other thing we're going to write about null hypotheses. We're going to come back to that. The second hypothesis is the alternative hypothesis. It is denoted as H sub A. This is the hypothesis that comes in and says, something's wrong. It is not what you claim. Now, when it comes to these hypotheses, the null is that expert claim, the alternative is you saying they're wrong, and as a result, the alternative hypothesis is the exact opposite of the null hypothesis. Because if you're trying to prove that someone is wrong, even if you have an assumption on what it should be, the best you can do is just claim that what they've said is just wrong. Even if you think you got a more specific, more accurate claim, that's not the goal of hypothesis testing. The goal of hypothesis testing is to say, you're wrong, even if you're the expert. Now, when it comes to each of these hypotheses, that null hypothesis always has some sort of equality. Now, that means that the expert is saying something is equal to this amount, or it's greater than or equal to this amount, or it's less than or equal to this amount. Regardless of which of those it has equality to it. While an alternative is a pure inequality, it has to be the opposite of the null. The opposite of something with an equal is something without an equal. What is the opposite of equal? Not equal. If the null says equal, your alternative is not equal. What is the opposite of greater than or equal to? Less than. If the null is greater than or equal to, the alternative is less than. Opposite of less than or equal to? Greater than. Okay, so you want to come in, you want to prove the expert wrong. To do so, I've kind of broken it down into 6 steps. Some are really, really quick steps. But it's one of the few things that throughout math I actually teach by giving you steps on how to do it. You probably noticed that there aren't many times where I break down and give you steps. Because generally speaking, I am a strong believer that when it comes to doing well at math, part of it is understanding where things came from. Hypothesis testing It's not a particularly challenging process, but it's got a number of components to it that you have to meet. First thing you have to do is just simply identify the hypotheses. That is both null and alternative. You have to identify them both. And technically, you should also recognize what is the expert claim. Now, I'll be honest with you, I'm not going to worry too much about the expert claim. Now, step 2 essentially has you choose, quote unquote, a significance level. Now, first off, I put choose in quotations because of the fact that you're never actually going to have to choose. I'm going to tell you in the problem what the significance level is. So you just have to recognize what it is. And what a significance level is essentially the threshold that you are going to pass in order to step in and say the expert is wrong. Now, in order to say the expert is wrong, something has to be extremely unlikely to be true for you to step in and say, even though you are the more knowledgeable on this subject, I can prove you wrong. So the probability of it happening at this low amount, it's going to vary from problem to problem on what is considered appropriate. Most commonly, there are 3 significance levels that are appropriate. They are 10, 5, and 1%. You can choose technically different significance levels out in the real world, but these are the 3 that we're really going to use here. These are the 3 percentages that are going to be our, it's less than a 10% chance of happening. Nope, I'm going to step in and say something's wrong. Or a 5%, or a 1%. Which percentage you use, for the sake of what we do, is really just going to be what's told to us. In the real world, which percentage you use depends upon the risk of being wrong. If something has a high risk of the expert being wrong, the significance level is not going to be as low because of the risks associated with the expert being wrong. If proving the expert wrong can cause issues, then they tend to lessen that significance level and say, no, you have to be 100% sure. Okay, obviously not 100% sure, more like 99% sure that they are wrong. Like, you have to really prove them wrong. So the significance level really is going to depend upon the importance of what it is that you're focusing on. Now, when we choose that significance level, we are also going to draw a bell curve that goes with it. And we're not going to draw a particularly specific bell curve. When we draw our bell curves, what's it going to look like is it's going to look like a bell curve. The outline, and then you're going to just have a tiny bit of it shaded. What bit of it shaded is dependent upon the alternative hypothesis. It's really there just to give us a guide of what we're looking at, and that'll get a little bit more clear as we get into the problems. From that, we're going to calculate a hypothesis z-value. Now, we've done a formula for z-values with normal distribution. Z equals X minus mu all over sigma. But that Z value requires mu and sigma. In other words, it requires information about the population, about every possible outcome. If you know information about every possible outcome, you're not doing a hypothesis test. You have the data necessary to be like, no, this is everything that we know. Take it or leave it. Hypothesis testing is done in situations where you don't have the entire population's data. What you have is information from a sample. So we have a different formula for Z then. The Z for hypothesis testing is given by the following formula. Z equals X var minus mu all over S divided by the square root of N. X bar is the sample mean. Now mu should be population mean, which just kind of brings to question what I just said. If you know everything about the entire population, you're just going to look at the population data. But it is the population mean, specifically based on the null hypothesis. Because the expert is the one saying, this is what the mean is of the population. That is what we're testing, if it's true or not. So we assume the expert is true for the formula, and then we prove them wrong. N is still sample size. S is sample standard deviation. Once you have the Z value, you can find the probability of that result happening. Using that normal Z chart. Keep an eye on if you're talking about a less than, a greater than, or a not equal to when doing this. And we'll talk about how to deal with not equal to, because we haven't dealt with that before. Y'all know how to deal with a Z chart, greater than or less than. Chart does less than, you have to look at the opposite to do greater than. You're then going to compare that probability with the significance level. Significance level I'm going to shorten down to SL for what I'm about to write. So the probability that you calculated is the probability of the sample having that information, assuming the expert is correct. So if the probability that you get is less than that significance level, that means the probability of those results coming out of that sample is so small, it's beneath the significance level, that you have enough information to then reject the null hypothesis. You can reject that there is nothing wrong in the situation. because you have the evidence. It's so unlikely that it will happen that you can step in and say the expert's incorrect. On the other hand, if the probability of it happening is above that significance level, essentially what's happened is you don't have the evidence. It doesn't mean that the expert is correct. It just means you don't have the evidence to prove them wrong. So you fail to reject H sub O. You fail to reject that there's an issue. If you prefer to think about it as accepting it, you can. But the reason we don't just straight up write accept is that it doesn't mean that there isn't a problem when you don't have the right probability. It just means you don't have the evidence to support that the expert is wrong. Last thing you have to do is just make a conclusion. Similar to yesterday, that means writing a sentence. Okay. Yesterday, I gave you a thing that had examples for both days of 11.6. So you're going to want to grab that out. Who needs one? Okay. So the first thing we're going to practice a little bit on is just identifying the hypotheses. It also says identify the expert claim. I'm not too worried about the expert claim. I already mentioned that. So, Jill thinks that she tells at least 5 jokes every class period. So when it comes to identifying your hypotheses, we got H sub O, we got H sub A. Both of these are going to be about the population mean. So both of these are going to be in reference to mu. Jill thinks she tells at least 5 jokes every class. What is at least 5 as an inequality? I see lots of mouths moving, but I do not hear a single word from anyone. Not exactly. At least, so that includes an or equal to, right? 5 is fine. Is it greater than or less than? At least is greater than. At least is the minimum that you're allowed to have. Mu is greater than or equal to 5. By the way, I'm not going to emphasize it, but I'm going to talk about it a little bit here, and then if you don't do it on your homework, I'm fine. Is Jill the expert? She's talking about telling jokes. Her telling jokes. Is she the expert of herself? Yes. So that would be the expert claim. That would be the null hypothesis. The alternative hypothesis is the opposite of that. What's the opposite of greater than or equal to? Just straight less than. Mindy thinks there aren't 35 peanuts in every package. Not 35. In math terms, we would say mu is what's not 35? It's not less than. It's just straight not equal to. Now, you might think that she's implying that there's less than 35, but that's not what it says. It just says not 35. So it's not equal to. Now, if it's not equal to, is that a null or an alternative? Which one has no equal sign to it? The alternative. The null hypothesis always has to have some sense of equality. That's why this one automatically went in null, because it was or equal to. Opposite of not equal to is equal to. Now, again, I don't care if you don't do it on your homework, but in all technicality, is Mindy the expert? Does it give any sort of implication that Mindy is the expert on peanuts? No. The expert would be probably the company. She's probably making this claim because she's stepping in and saying, the packet says it's supposed to have 35, but it doesn't. So, Mindy is not the expert. The expert is the one that said it was 35. Okay, now, before we get into our actual problems that have us doing the entire process, we need to talk a little bit about how these hypotheses deal with the bell curve. So in all technicality, when you are doing hypothesis testing, there are 3 different forms of hypotheses tests. There is, okay, they kind of break it down as one. They break it into these 2, which are considered one-tailed tests. A one-tailed test is the situation where you have a alternative hypothesis where mu is less than some number. And we're just going to say, I'm just going to put a number symbol. You also have the situation where mu is greater than a number. In the situation where it is less than, it's technically called a left-tailed test. Over here you have a right-tailed test. It really just focuses in on what side of the graph your alternative hypothesis fits. It fits over here when it's less than, because of the fact that in a situation where your alternative hypothesis is less than, that means the expert claim is greater than or equal to. And so, you are able to step in and prove them wrong if you have enough evidence to prove that it's that less than. And so what you're going to end up doing then is looking for the probability of a z value being less than whatever you get for a z. I'm just going to put c there. A right-tailed test is the situation where your alternative hypothesis is greater than. That means the null hypothesis would have started as a less than or equal to. So the expert claims that it should be this number or smaller. You chime in and say, I have enough evidence to prove that it's actually larger by finding the probability that z is larger than that specific z value that we end up finding. Now the two-tailed test is the one in the middle. This is where you have mu not equal to some number. It's called a two-tailed test. Two-tailed test is the one that causes the biggest issues. This is the situation where the expert claims that it is exactly equal to something. You're trying to prove that it could be either greater than or less than. Which you're trying to prove is going to depend upon your data. If your data shows that it's greater than, you're going to prove that the probability of it being greater than is too small. If your data shows that it's less than what it should be, you're going to prove that it's the probability of it being less than it. So what ends up happening is there are two regions that are what are called the critical regions. The critical region is that area of the graph that fits that tiny little probability that you're trying to show it is. In a 10% significance level, you're trying to show that the probability of it happening is less than 10%. In a left-tailed test, that means you're showing this piece, that it fits somewhere over here where this is the bottom 10% of the data. In a right-tailed test, you're also trying to show that the probability is less than that significance level. But in this case, you're showing that the number is bigger than what it should be. And so this is the top 10%, if the significance level is 10% of the data. But when it's in a two-tailed test, what ends up happening is your significance level gets cut in half. Part for down here, part for up here. And if you're doing a 10% significance level, that means 5% of it's down here, 5% of it's up here. And when you make your comparison of probability on a 10% significance level two-tailed test, you're actually going to end up comparing to 5% because the significance level got cut into two regions. One region, this lower region, where you're looking at the probability being less than something, you do that in situations where z is negative. If the z value you calculate is positive, then you're looking to see if it's in this upper region. This, explaining that two-tailed test, is the place where it gets the most confusing. So if you're sitting here and being like, what? If you got to that point earlier, I swear it makes more sense once we start doing a problem. But if you were able to follow me until we got to here, you're in good company. That tends to be where it starts to have issues. And it makes more sense once we do an example. So, trust the process. Let's get into an example. Lindsay, the president of student council, has heard complaints that the cafeteria lunch line moves too slowly. The dining service coordinator assures her that the average wait time is 6 minutes or less. Using a sample of 65 customers, Lindsay calculated a mean wait time of 6.3 minutes and a standard deviation of 1.1 minutes. Test the hypothesis at a 5% significance level. So, Lindsay is trying to prove the dining service coordinator wrong. Dining service coordinator is the expert on the situation. Lindsay, president of student council. Someone doing a little bit of research. First thing you got to do when you're doing hypothesis testing is identify your hypotheses. The null hypothesis is the claim that nothing is wrong. It should come from the expert. Who was the expert in the situation? The coordinator. What did the coordinator say was true? 6 minutes or less. Does that include an or equal to? Yes, as it should, because that should be the null hypothesis. Is it less than or equal to or greater than or equal to? Less than or equal to. Mu is less than or equal to 6. That means the alternative hypothesis is greater than 6. There's step 1. Step 2 says choose a significance level and make the bell curve. Significance level is chosen for us. In this case, it is 5%. In other words, Lindsay has to show that the probability of her getting this data is less than 5% chance of happening. Draw a little bell curve that goes with it. That little bell curve bases itself on the alternative hypothesis. Really, all you're trying to do with this bell curve is you're either going to be shading a small part on the left of it, a small part on the right of it, or a small part on both. Which you do is based on where the alternative hypothesis is going to go. According to this, the alternative hypothesis is greater than, which means we want to be on the right side of the graph. Because when it comes to a normal bell curve, the greater than 5% piece is way over here. That area essentially on our graph represents the 5% of the time that we're throwing up red flags. That's where the probability should be less than 5% when it's above that level. So, step 3 says calculate the z-value. Hypothesis z-value, x bar minus mu all over s divided by the square root of n. What's x bar? .3 sample mean. What's S? Sample standard deviation, yep, 1.1. What's N? 65 sample size. So 6.3 minus something over 1.1 divided by the square root of 65. That something tends to be one thing that messes with people. Mu is the population mean according to the expert. According to the expert, it is less than or equal to 6. For the threshold, we just write 6. I could type that into a calculator. It's very calculator friendly if I put what on it? Parentheses where? Top and bottom. It is a z-value. How many decimal points should I go to? 2. Because z-values go into the pink chart, the only way it can go into the pink chart is if you have 2 decimal places. Make sure you are rounding appropriately when you calculate your z-value. And what do we get for a z-value? Hint, it starts with 2. 2.20. Because of the fact that our alternative hypothesis is a greater than, we shaded this part of our graph, which means we're going to do the probability that z is greater than that value. Does my pink chart do greater thans? Not directly. How do we make it do greater thans? Look on the opposite number. Instead of looking at 2.20, I'm going to look at negative 2.20. You don't have to write that down, but that's where we're getting this from. Negative 2.20. 0.0139. That means the likelihood that Lindsay got the result of 6.3 minutes with the standard deviation of 1.1 is a 1.39% chance of the expert being right and her getting those results. Is that particularly likely? No. We compare it to our significance level. What was our significance level again? 5%. Would you agree that 1.39% is less than 5%? If the probability of it happening is less than the significance level, is that when we raise a red flag, or is it the opposite? It's when it's less than. When the probability that we get is less than the significance level, that means it's so unlikely it shouldn't happen. We reject the null hypothesis at this point. In other words, we tell the expert, you are wrong and I have the proof. So, last thing we do is we conclude. Essentially, you state there is enough evidence. Your claim will always essentially say there is or there is not enough evidence to reject, and then it's just whatever the H sub O actually is, but in words. Mu is less than or equal to 6. What was less than or equal to 6? What is it actually measuring? Wait time. There's enough evidence to reject that the wait time is less than or equal to 6 minutes. We have the evidence. You are wrong, Miss Dining Service Coordinator. So, a lot of stuff leading into it. Individual calculations don't tend to be bad. This is the piece that tends to trip people up, if anything. And it's always based on that alternative hypothesis on what you're looking at for greater than or less than. Okay. We're just doing one more example. Question 6. Jared wants to determine if each pizza indeed has 100 pieces of pepperoni. Using a sample mean of 42 pizzas, Jared calculated a mean of 99.8 slices and a standard deviation of 0.8. Test the hypothesis at a 5% significance level. Step 1. Identify each of the hypotheses. Both of them are referencing mu. He wants to determine if each pizza indeed has 100 pieces. When he says indeed has 100, doesn't it sound like someone must have said it has 100? How do you say it has 100? Equals 100. Should that be the null or the alternative? If it has an equals, it's null. Null is the equal one. The alternative is Jared essentially coming in saying, does it really? Does it really? And the opposite of equals is not equals. Significance level is 5%. Bell curve, when it's a not equal to, shade both sides. Our significance level gets cut in half when you shade both sides, because the shaded region represents the 5% of the time that we're going to be able to step in and say they are wrong. But it got split between the situation where it's greater than and where it's less than. So when we do our comparison later, we're not going to compare to 5, we're going to compare to 2.5. Because once we have our data, we're going to end up with a situation where either we have fewer than 100 pepperoni or more than 100 pepperoni. And so we're going to end up trying to see if our number lies in this range because there's more than 100, or in this range because there's less than 100. You probably already know which one we're ending up in, because what's the sample mean? $99.8. So are we ending up with a greater than situation or a less than situation? We're already less than what it should be. Which means we're going to actually end up over here. When over here, you do the probability that z is less than. When over here, you end up doing the probability that z is greater than. Standard deviation is 0.8, sample size is 42. We calculate z. Hypothesis z, again, is a different formula, because you're not working with a population, you're working with a sample. It's x bar minus mu all over s divided by the square root of n. It is calculator friendly, assuming you have parentheses where again? Top. What do you get for a z value? Negative 1.62. I'm just going to write a little note here. In a two-tailed test, greater than or less than depends upon if z is positive or negative. If z is negative, you are going to do less than that value. Because you're trying to see if it fits in this lowest 2.5% of the possibilities. Because it definitely is not going to show up over here if it's a negative z. What's the probability of that happening? In other words, what do you get on your chart? 0.0526. Got a 5.26% chance of Jared getting this data, even if they're supposed to be 100%. Or even if there's supposed to be 100 pieces of pepperoni on every pizza. My significance level is technically 5%, but in a two-tailed test, I break it in half and I compare to 2.5%. Would you agree that 5% is greater than 2.5%? Which means it didn't meet our threshold for saying the expert was wrong. We needed it to be less than 2.5% likely to be on this smaller end, or we needed to be less than 2.5% likely to be on the larger end. But the data didn't end up on the larger end at all. So, we failed to reject. If you prefer to just go with accept, that's fine. Technically, it's not 100% correct because you can't prove that an expert is right using hypothesis testing. You can only prove them wrong. We conclude. In this case, when you fail to reject, you say there's not enough evidence. There's not enough evidence to reject, and then what would you have been rejecting? What was the null hypothesis? Each pizza has 100 I'm getting lazy and just writing pepperonis. Technically, it should be pieces of pepperoni.